Good afternoon, everyone. Good afternoon. Could you please press the thumbs up sign if you can hear me clearly? Okay, thank you very much. So again, good afternoon, everyone. I would first like to note that this webinar is being recorded and is being streamed live on YouTube, and the link will be posted on the Institute of Mathematics Facebook page. Okay. So welcome, everyone. I'm glad you can join us again for the IMath Webinar series. I am Gino Angelo Velasco, the coordinator for research of the Institute. So to those who are new here, we will be having different mathematical talks throughout the semester around every other week. And after each talk, there will be time for some questions. So you just raise your hand to ask a question, or you can type your question in the chat box. So here or on YouTube. So yeah, let's start. Today's talk will be presented by Dr. Ramon Inigo Marfil of the Mathematical Finance and Actuarial Science Group of the Institute. The title of his talk is On the Placing Probabilities and Expected Time Until Ruin for the N-Tower Problem using recursions based on multigraphs. Okay, so let us all welcome Dr. Ramon Marfil. So Ramon?
Thank you, Sir Gino, for the introduction. Good afternoon, everyone. So for today's webinar, I will be talking about my PhD dissertation on the placing probabilities and expected time until ruin for the N-Tower problem using recursions based on multigraphs. So first, we will define some basic concepts. Tingnan natin kung ano yung background ng problem na to. And we will then look at the methodology, kung paano sinolve yung problem, kung paano minodel and sinolve yung problem. And we will also look at some of the interesting results that were obtained in this research. Okay. So first, we look at the gambler's ruin problem. So for the basic gambler ruins problem or gambler's ruin problem, we have one player. Consider a gambler with starting wealth A, say $100, and each round, that player bets a fixed amount, say $1 on a fair game. So fair game, ibig sabihin, that player has an equal chance of winning or losing that game. So 50-50 yung chance niya of winning or losing that game. That player keeps playing until that player achieves a target amount, and in most cases, the target amount is twice the starting amount, or for simplicity, sabihin natin doble nung starting amount, yung target amount niya, or lose all their money. Kasi maubos lahat ng pera niya. So the usual problems for this, or the usual questions for this type of problems are number one, what is the probability of winning for each player? And number two, what is the expected game duration, or what is the expected time until ruin or success? Okay. So for the basic gambler's ruin problem, the probability of winning of that one player is A over N, which is simply the ratio of the wealth of that player to the target amount. So kung $100 tsaka $200 yung starting wealth and yung target amount, the probability of winning for that player is 1/2. And the expected game duration, denoted by T, is equal to A times the quantity N minus A. Now we can extend this problem to a two-player gambler's ruin problem. So for the two-player gambler's ruin problem, consider two gamblers playing a fair game against each other, each time betting 1 unit. So again, fair game, so each player has an equal chance of winning or losing. If the gambler's initial wealths are A and B respectively, then from the first gambler's perspective, this is simply the one-player gambler's ruin problem kung saan yung target amount niya ay A plus B. Maubos yung pera nung kalaban niya. So the target amount is A plus B. So in solving the two-player gambler's ruin problem, pwede natin tingnan yung pag-solve nito in one player's perspective. So For example, gambler one's probability of winning is simply A over A plus B, or the ratio of his wealth to the total wealth of all players, or in this case, the two players. And the expected game duration is T equal to the product A times B. Now we can keep extending this by adding and adding more players. So we have, for example, an n-player gambler's ruin problem. So consider n gamblers with initial wealth S sub 1 up to S sub n, respectively, playing a fair game against each other. So in this case, gambler I's probability of winning is that gambler's initial wealth, S sub I, the ratio of that player's wealth, S sub I, to the total wealth of all players, summation of S sub n, with small n ranging from 1 to capital N. And gambler I's probability of ruin depends on the game structure. So there are different game structures depending on the number of players selected in each round, kung pwede bang lahat sila involved dun sa round na yun, or pipili lang ba tayo ng 2 players at a time, and so on. So maraming mga types ng games, or maraming game structures para sa n players. So for my research, ang ginawa ko ay nag-focus ako doon sa tinatawag na n-tower game. Okay? So what is the n-tower game? So the n-tower game, or in the n-tower game, consider a game where each round has one winner and one loser, and each game involves exactly 2 of the n players, say players I and J. So kunwari meron kayong 5 players, in each round, 2 players lang yung pipiliin natin para maglaro. So kunwari players 1 and 2. So after one betting round, the new states are shown by the following map. So ang nangyayari ay, kunwari si players 1 and 2 yung involved, players 1 and 2 each have an equal chance of winning against each other. And in each round, ang posibleng mangyari ay, kunwari pag nanalo si player 1, makakakuha siya ng 1 unit of wealth or 1 chip mula kay player 2. Kung matalo naman siya kay player 2, magbibigay siya ng 1 unit of wealth or 1 chip kay player 2. So 1 unit of wealth yung natatransfer kada round. And each round will involve only 2 players. Okay? So yun yung n-tower game na kung saan tayo magfo-focus para sa research na to. So what were the other researches done in topics similar to this? So in 2002, Bruss et al. Used martingales in giving an asymptotic solution to the 3-tower problem. So sa solution nila, gumamit sila ng triangles and trigonometric functions. Kaya nahirapan silang i-attempt na i-generalize yung solution nila to the n-tower problem. So limited lang yung algorithm nila, or yung process nila of solving to 3 players. Okay? 4 years later, Swan and Bruss developed a matrix analytic approach in solving general n-player problems, and they used folding algorithms for efficiency. So nag-construct sila ng mga lattices, and yung lattices nila dinivide nila into several levels. Tapos ang ginagawa nila doon ay para mas mabilis nilang ma-solve yung problem, hinati nila or fina-fold nila yung lattice para kumonti yung levels para mas maging simple yung pag-solve dun sa problem. And later on, they will unfold or ibabalik nila by some recurrence para ma-solve nila yung main problem. And one limitation for their research is they cannot solve for player equities if the game has payouts beyond the first place. So kaya lang nilang isolve yung probability ng pag-place ng first and last ng bawat player. Hindi nila kayang hanapin kung ano yung probability of placing second, third, and so on. So yun yung isa sa mga limitations ng research nila na gagawa natin ng paraan dito sa research natin. And in 2014, David used multigraphs and recursions to solve the three-tower problem. So mula dito sa paper na to, kinuha yung algorithm na ginamit ko para dito sa research na to. Tapos in-extend ko na lang siya to solve to solve problems involving n players. And para magawa natin yun, gumamit tayo ng mga recursions. Okay? Or ng additional recursions doon sa algorithm. Okay? So, ano yung main problem natin for this research? So the main purpose of this research is to solve the placing probabilities of each player for the n-tower problem. And to be more specific, this research aims to do the following. Number one, construct a weighted directed multigraph for the n-tower problem with prescribed total wealth S. Sunod, we construct an appropriate linear system that represents the multigraph for the n-tower problem with prescribed total wealth S. So describe natin base dun sa multigraph, ano yung linear system na makukuha natin kung saan yung linear system na yun yung isosolve natin para mahanap yung placing probabilities natin for the n-tower problem. So number three, develop a numerical algorithm for solving placing probabilities for the n-tower problem with a prescribed total wealth S. And number four, present a method for calculating the expected time until ruin for the n-tower problem with the prescribed total wealth S using the numerical algorithm in the previous step. Okay? So para dito, meron tayong mga ilang ide-define kung ano ibig sabihin ng multigraph, kung ano yung mga Markov chains na gagamitin natin. And yun yung mga ide-define natin ngayon. So first, what is a weighted directed multigraph? So for this, define muna natin kung ano ibig sabihin ng graph. So a graph G with elements V and E consists of two types of elements. So yung V ay yung vertices, yung E naman ay yung edges. And every edge has two endpoints in the set of vertices. Pag sinabi naman nating weighted yung graph, ibig sabihin merong weight or number associated with each edge. So ibig sabihin, or in this case, or in this research, yung weight or yung number na yun ay yung probability of transition between states. Okay? Sunod, directed graph naman, a graph where all edges are directed from one vertex to another. So ibig sabihin, merong direction. So merong initial edge, tapos merong terminal edge, or merong final edge. So merong pinanggalingan, merong pupuntahan yung bawat edge natin doon sa graph. And those will describe the transitions between the possible states in our problem. And multigraph naman, ibig sabihin, this is a graph which may have multiple edges connecting the same pair of vertices. So pag sinabi nating weighted directed multigraph, i-combine lang natin lahat ng mga definitions natin. Now, we will also need the concept of an absorbing Markov chain. So given a set of states S with states S sub 1 up to S sub n, a Markov chain is a process satisfying the following conditions. The transition probability P sub ij of moving from state I to state j depends only on the current state S sub I. Meaning, sa Markov chains, hindi nagmamatter kung ano yung mga previous, yung mga steps bago nung current state. So hindi nagmamatter kung anong pinanggalingan niya. Ang titingnan lang natin ay kung saang step siya nanggaling or kung saang state siya nanggaling in the previous time step. Okay? So yun lang nagmamatter, yung pinakahuli. Hindi nagmamatter kung ano yung step before that or yung step 2 units of time before that. Okay? Sunod, the sum of all transition probabilities from S sub I is equal to 1. That is summation of P sub ij with I ranging or with j ranging from 1 to n is equal to 1. And meron din tayong tinatawag na absorbing state para sa Markov chain. So A state S sub I is called an absorbing state if the probability of transitioning from that state to itself is equal to 1. So absorbing state, ibig sabihin, kung naabot na natin yung state na yun, ibig sabihin, doon na tayo forever. So hindi na siya makakaalis doon sa state na yun. Okay? And an absorbing Markov chain satisfies the following conditions. Number one, it has at least one absorbing state. And number two, it is possible to go from any state to at least one absorbing state in a finite number of steps. So yun yung isa sa mga unang types ng states natin. Meron tayong absorbing state. So pangalawa, meron tayong tinatawag na transient state. So a state S sub I is called a transient state if it is not an absorbing state. So basta hindi siya absorbing state, transient state na yung tatawag natin sa kanya. And suppose that there are T transient states and R absorbing states for an absorbing Markov chain. The transition matrix will have the following canonical form. So meron tayong matrix na ganito yung itsura. Meron siyang apat na submatrices, Q, R, zero matrix, and identity matrix. So Q here is a square matrix, T by T matrix siya. Yung R natin ay non-zero T by R matrix. Yung zero dito ay isang R by T zero matrix. So puro zero yung mga elements niya. And I here is an identity matrix, which is R by R. Okay. And in this case, the first T states are the transient states, while the last R states are the absorbing states. So yung transition matrix will describe the transitions from the name, the transitions among states in the Markov chain. So yung submatrix Q describes the transitions among transient states, yun yung T by T square matrix natin. Yung R naman ay yung submatrix R describes the transitions from transient states to absorbing states. Yung I ay ito yung transitions from absorbing states to themselves. Alam natin from the previous slide na kapag absorbing state siya, doon na siya forever. And zero naman, meron tayong zero submatrix dito dahil imposible namang makapunta mula sa isang absorbing state pabalik sa isang transient state. Kaya siya zero matrix dito. Okay? And for an absorbing Markov chain P, the matrix N, which is equal to the inverse of I minus Q, is called the fundamental matrix for P. And the entry N sub ij of N gives the expected number of times that the process is in the transient state S sub j if it started in the transient state S sub I. Okay, so yung mamaya makita natin kung paano gagamitin to sa pag-calculate ng expected time until ruin para doon sa n-tower problem. Okay. Now, for the n-tower problem, we also have the following definitions. So first, a chip state is an ordered n-tuple S sub I up to S sub n, where S sub I up to S sub n are non-negative integers. So the elements of a chip state represent the wealths of each player at a given time. Okay? So anong example niyan? Bigay tayo ng example. So for example, we have magsulat. For example, we have 4 players na yung wealths nila ay 4, 3, 2, and 1. So a chip state is an ordered n-tuple. So itong ordered n-tuple na yan, or yung ordered quadruple na to, is a chip state. Okay? For the case where we have 4 players and yung total wealth nila ay 4 plus 3 plus 2 plus 1, which is 10. Okay? Now, a chip position is an element of a chip state, S sub 1 up to S sub n. In this case, the chip positions are S sub 1 up to S sub n. In this case, in this specific example, yung chip positions natin ay 4, 3, 2, and 1. Next, a terminal state is a chip state where at least one chip position is 0, and a non-terminal state is a chip state where all the n chip positions are positive. In this example, 4, 3, 2, 1, meron tayong 4 na positive chip positions. Ibig sabihin, this is an example of a non-terminal state. So ibig sabihin, ang ibig sabihin ng non-terminal state ay hindi pa tapos yung laro. Ibig sabihin, ongoing pa dahil lahat ng players natin involved ay meron pang at least 1 unit of wealth. Okay? An example of a terminal state is pwedeng 4, 3, 3, 0. Halimbawa, kung saan yung fourth player, 0 na yung wealth niya. So dahil doon, alam natin na 3 players na lang yung may chips dito or yung may wealth dito. So ibig sabihin, this scenario will be reduced to a 3-player problem instead of 4 players. Okay? So next, ano bang gagawin natin sa methodology natin? So for our methodology, ang gagawin natin ay first, we generate unique states for a given wealth total S. So kunwari kanina, yung total wealth natin ay 10, kukunin natin lahat ng possible unique states with total wealth N. Okay? And for the multigraph, ang gagawin natin ay i-arrange na natin yung mga positions in decreasing order of the in decreasing order. So ibig sabihin, yung state na kapag meron tayong state na 4, 3, 2, 1, saka halimbawa 4, 3, 1, 2, for purposes of graphing, pareho na lang sila. Okay? Or pwede ring 3, 1, 4, 2. So lahat sila ika-clump natin or pagsasamahin natin, isusulat natin sila sa graph bilang 4, 3, 2, 1 na lang for simplicity. Okay? Sunod, our next step, we will use a multigraph to show transitions among states. So we will draw edges between these states. Number 3, we will construct matrices representing transitions using a theorem or using theorem. And number 4, we will solve the linear system for the placing probabilities of each player. And yung step 4 na to will involve a recurrence of the algorithm that we will use. Dahil hindi natin kayang ma-solve yung placing probabilities using just one iteration, so gagawin natin siya by reducing the number of players by 1 in each iteration. And last step is we calculate the expected time until ruin using absorbing Markov chains. So para mas malinaw to, let's look at an example. So for the case where we have 4 players, so n is equal to 4, and the total wealth S is equal to 6, construct natin yung multigraph para dito. So para dito, let's construct the multigraph. So una, construct natin yung mga terminal states for the 4-tower problem. So terminal states for the 4-tower problem are the states where the fourth position is equal to 0. So ano ba yung mga positive integers na nag-add up to 6? We have 411, 321, and 222. So a fourth state is equal to 0. And for the next column, ilalagay naman natin yung yung mga states kung saan yung last position natin ay 1. Okay? So we have 3111 and 2211. And for n equal to 4 and s equal to 6, there are no other possible states. So ito na yung lahat ng yun. Next, we will construct the possible transitions among these states. So yung mga transitions natin, manggagaling lang sila dito sa mga non-terminal states. Dahil kapag terminal states na lang sila, na-reduce na natin sila to 3 players and magiging iba na yung graph para doon. Okay, so ano ba yung mga transitions natin for these states or from these states? So, for example, for 3111, ano yung mga posibleng mangyari? So, for 3111, halimbawa magkalaban yung dalawang players na yung isa ay may wealth na 3, tapos yung isa ay may wealth na 1. Ibig sabihin, ang posibleng mangyari ay yung first player yung manalo. So kung yung first player yung mananalo, yung wealth niya magiging 4, the loser will have wealth 0. So there are 3 possible ways of doing that from this state to this state. Okay? Or wait, dito pala yan, dito yan. Wait. 3111, dito papunta. 4110 dahil kapag nanalo yung first player, mauubos niya yung wealth ng either player 1, player 2, player 3 or player 4. So yun yung magiging yung player na may 0 wealth, yun na yung 0 dito. Okay? Posible rin naman na si 3 tsaka si 1 yung magkalaban, pero si 1 yung mananalo. In that case, pag si 1 yung mananalo, or pag si 1 yung nanalo, ang mangyayari ay si 3 magbibigay ng 1 unit of wealth sa kanya. So, ibig sabihin, yung wealth nila pareho magiging 2. So, there are 3 possible ways of transitioning from this state to this state kapag ganun yung magkalaban. Si 3 tsaka si 1. Okay? Ngayon, ano pa yung ibang posibleng mangyari? Pwedeng dalawang 1 yung magkalaban. Okay? So kung dalawang 1 yung magkalaban, ang posible lang mangyari dyan ay yung mako-combine yung wealth nila, magiging 2, tapos yung losing player, mawawala na yung wealth niya. So magiging 0 yung wealth. Magkakaroon tayo ng 6 na transitions or 6 na edges mula dito papunta dito. Okay? And doing the same for the state 2211, it is possible to transition from this state to this state. Posible rin na papunta dito, and posible rin na papunta siya dito sa 2220. Okay? So there are 3 unique terminal states. Tawagin nating P sub 1, P sub 2, and P sub 3. So ito yung P sub 1, P sub 2, P sub 3. Meron tayong dalawang unique na non-terminal states. Tawagin natin P sub 4 and P sub 5. Meron tayong 4 na unique na non-terminal positions, V sub 1 up to V sub 4. So ano-ano yung non-terminal positions na yun? First, ito siya. Wait, gamit tayo ibang color. So V sub 1, V sub 2 yung 1 unit of wealth. V sub 3 naman yung 2 dito. Tapos V sub 4 yung 1 dito sa state na to. And we also have 9 unique terminal positions. So ito yung W sub 1, W sub 2 yung 1 dito, W sub 3, and so on. So 4, 5, 6, 7, 8, and 9. Okay? So kung basta magkapareho sila ng wealth in the same state, counted sila as one unique terminal or non-terminal position. Okay? So ito yung multigraph natin for the case where n is equal to 4 and s equal to 6. Now, ang gagawin natin, sunod, ay i-construct natin yung linear system for n equal to 4 and s equal to 6. So after constructing the multigraph for a given wealth total s, a linear system I minus q times b equal to r, representing the transitions between the states, is constructed. For this example, the linear system for n equal to 4 and s equal to 6 is shown below. So yung mga numbers dito, yung mga entries ng matrices dito, represent makukuha natin to base dun sa number of edges na nakuha natin or na-construct natin in the previous slide. Okay? So, ito yung mga V sub 1, V sub 2, V sub 3, up to V sub 4. Ito naman yung W sub 1, W sub 2, hanggang W sub 9. So, this will represent the transitions from non-terminal positions to terminal positions. Okay? Ito yung transitions between or among non-terminal positions. Okay, kaya siya 4x4 matrix. Ito yung matrix Q natin doon sa canonical form. Okay? And dahil doon, kaya dito sa equation na to, or dito sa linear system na to, kaya na nating isolve yung B dahil non-singular naman yung I minus Q. Okay? And the solutions to the system is an n by m matrix that gives absorption probabilities for the n unique non-terminal positions into the m unique terminal chip positions. Okay, so pag sinolve natin yung B dito, it has the following solution. Okay, so recall, so para lang malinaw ito yung V sub 1 natin, V sub 2, V sub 3, and V sub 4. Tapos ito yung W sub 1, W sub 2, and so on up to W sub 9. Okay, ito yung mga non-terminal chip positions. Ito yung unique terminal chip positions sa taas. Okay? And anong sinasabi ng entries natin dito? Or ano yung posibleng maging interpretation natin dito sa entries na to? Ang sinasabi dito sa matrix na to ay kunwari dito 0.257 yung first entry dito. This means that for V sub 1, yung 3 natin in the state P sub 4, its probability of ending up or being absorbed in the terminal chip position W sub 1, or the position 4 in the state 4110 is 25.7% and so on. Okay? So kung nag-start kayo with 3 units of wealth, tapos yung tatlong kalaban nyo ay puro 1, yung probability nyo of ending up with in the state 4110 with wealth 4 is 25.7%. Okay? So in this case, makukuha natin yung transition mula doon sa non-terminal positions papunta sa terminal positions. Okay? Now, to calculate the players' placing probabilities, we need the solutions to the 3-tower problem for S equal to 6. Dahil dito, ang nasolve pa lang natin ay ano yung probability nung bawat player na mag-end up doon sa bawat specific na position doon sa terminal positions natin sa 4-player problem. Okay? So, kung ganun, para ma-solve natin yung placing probabilities ng bawat player, kailangan natin yung solutions para sa 3-tower problem. So, ibig sabihin, we apply the algorithm to the 3-tower problem for S equal to 6. So, babawasan na natin ng isang player dahil na-eliminate na natin yung player na yun dahil 0 na yung wealth niya. So, doing the same, constructing the multigraph for n equal to 3 and S equal to 6. So, ito yung mga non-terminal states natin. Ito yung terminal states natin rather. Ito yung non-terminal states natin. Construct the edges using the same rules as before. Ito yung makukuha nating transitions. And we have these numbers. So, meron tayong tatlong terminal states, tatlong non-terminal states. Meron tayong 6 na non-terminal positions, yung 4 tsaka 1, 3, 2 tsaka 1 dito, tsaka yung 2 dito. Meron tayong 8 unique terminal positions galing dito. So 510, 420, and 30. Okay? So applying the same algorithm to this scenario, we have this linear system, and solving this linear system for C, again, non-singular itong matrix na to. Ibig sabihin, nag-exist yung solution natin para sa C. So, ibig sabihin, By solving that system, ang makukuha natin ay itong matrix na to. And ganun pa rin yung magiging interpretation natin doon. So kapag nag-start kayo dito sa 4, sa 411, the probability of ending up in 5, for example, in the state 510 is 36.2%. Okay? And again, to calculate the player's placing probabilities, kailangan nating ulitin ito. Kailangan natin i-apply ulit yung algorithm para ma-solve yung two-player game or yung two-tower game for S equal to 6 for the same wealth total. Okay. Now we have the following matrix X, whose entries are the probabilities of finishing in ith place for the corresponding positions in the three-tower game. Okay? So, ito siya. Mag-add lang tayo ng, dito, yung 0, kapag three-tower game siya, kapag, kunwari, 510 dito, nag-add na tayo ng, or 1 yung probability niya ng third place dahil siya nga yung unang naubos yung wealth doon sa 3 players na yun. So, ibig sabihin, sure tayo siya yung third place. Okay? Now, in 2 players, kunwari, 5 tsaka 1 yung wealth nila, it is known from the two-player gamblers win problem na yung probability of winning ay 5/6 para kay player na may wealth na 5. Probability naman nung player na yun of losing to the player with starting wealth 1 is 1/6. Kung maalala nyo, this is from the second slide earlier. Yung ratio lang nung wealth ng bawat player to the total wealth of both players or the sum of the wealths of those players. And the rest of the entries are calculated in the same manner. Okay? So pag umabot na tayo sa two-player game, yun, alam na natin yung solutions para doon. So we can use those values to solve the three-tower game and so on. Yung pag alam na natin yung solutions para sa three-tower problem, kaya na natin gamitin yung solutions na yun para i-solve yung four-tower problem. And yun, nasolve na natin recursively yung example na to. So using C in equation 8 and X in equation 9, we get matrix Cx, whose entries are the placing probabilities for each non-terminal chip position for the three-tower game. So, ibig sabihin, sa three-tower game, kung nag-start kayo with wealth 4, doon sa state na 411, ito yung probability of placing first, second, and third na makukuha natin by multiplying the matrices C and X. Okay? And the rest of the entries here can be interpreted as well in a similar manner. Ngayon, iaakyat natin to para ma-solve yung four-tower game. So from the previous matrix, we get the matrix W for the four-tower game by adding rows for 0 positions and a column for fourth place probabilities. So kapag meron kayong 0 dito sa four-tower game, ibig sabihin siya yung nag-fourth place doon sa state na yon. So kaya 1 yung probability niya of placing fourth. And the first, second, and third place probabilities are obtained from the solutions in the three-tower problem. Kaya tayo nagsisingit ng mga zeros dito, saka ng mga 1 entries doon sa 0 positions in the four-player problem or for the four-tower problem. Okay. Finally, using B in equation 6 and W in the previous slide, we get matrix BW, whose entries are the placing probabilities for each non-terminal chip position for the four-tower game. So ito na yung solutions na hinahanap natin para sa placing probabilities. This means that, for example, for B sub 1 for 3 in the state 4111 in the four-tower problem, its probability of placing second is 33.82%. Probability of placing first is 50%, placing third naman ay 13.36%, and placing fourth ay 2.82% lang. Okay, so yan, nasolve na natin yung placing probabilities para sa para sa 4-tower problem with total wealth equal to 6. Now, to solve for the expected time until ruin, we will use, let's recall the canonical form for the absorbing Markov chain. So recall that an absorbing Markov chain P has the following canonical form. Ito yung mga submatrices natin. And the submatrices represent the transitions between transient states and absorbing states. Okay? Dito sa problem na to, yung transient states natin ay yung positions in non-terminal states. Yung absorbing states natin ay yung positions naman sa terminal states. And for an absorbing Markov chain P, the matrix N is called the fundamental matrix for P. And we have this theorem na given an absorbing Markov chain P with N as its fundamental matrix, and P starts in state S sub I, we let P sub I be the expected number of steps before the chain is absorbed. So expected number of steps, ibig sabihin, ito yung number of rounds bago may matalo or bago may player na may maubos yung wealth. Okay? And let P be the column vector whose ith entry is T sub I. Then T is equal to the product of the matrices n times 1, where 1 is the column vector whose entries are all 1. Okay? So binibigyan lang tayo ng paraan ng pag-solve ng expected time until ruin gamit yung fundamental matrix. So essentially, ang sinasabi lang natin dito sa theorem na to, kapag alam na natin yung fundamental matrix ng isang absorbing Markov chain, ang gagawin lang natin ay i-add lang natin yung entries, lahat ng entries doon sa row, sa bawat row, and yung sum ng entries para sa bawat row, yun na yung magiging expected time until ruin, given your initial state S sub I. Okay. So using this example, n equal to 4 and s equal to 6 pa rin, we have the following matrix Q. Fundamental matrix natin is equal to this. And kapag in-add natin yung mga entries na yan, so add nyo lang yung mga entries sa bawat row, makukuha natin ay 22 over 15 for the first two rows, and 28 over 15 naman para doon sa last two rows. Okay? And magkapareho yung first two and yung last two rows dito dahil yung mga rows na yon represent positions in the same state. So kunwari, yung first two rows represent the positions, expected time until ruin for the positions 3 and 1 from this state. And last two naman ay yung para sa positions 2 and 1 mula sa state na to. So kaya sila equal. Yung 22 over 15 dito sa first two and 28 over 15 for the last two. Okay? And notice, mas malaki yung expected time until ruin para dito sa state na to, sa 2211 compared dito dahil if we start with the state 3111, mas expected natin na mas mabilis maruruin or mauubos yung wealth ng mga players dahil meron tayong tatlong players dito na may wealth na 1. So ibig sabihin, one game lang or one loss lang yung kailangan nila para maubos yung wealth nila. Kaya mas maikse yung expected game duration or expected time until ruin kapag nag-start tayo sa state na to. Okay? Now, for the other results, we have this comparison with the independent ship model. So yung independent ship model, isa siya dun sa mga, or siya yung pinakamadalas gamitin para sa pag-estimate ng placing probabilities ng mga players, kung saan yung mga wealth ng mga players ay pinaglalaban. Yung kunwari dun sa n-tower problem. So yung independent ship model is one way of calculating these placing probabilities, and the independent ship model depends only on the proportions of the chips or the wealths of the players. So kung makita natin dito, meron tayo mga states na multiples ng 4, 3, 2, 1 yung mga positions. So meron tayong 4, 3, 2, 1, 8, 6, 4, 2, and so on. Makita natin for ICM or for the independent ship model, para sa lahat ng states na to, equal yung probabilities, yung estimated probabilities, placing probabilities for first place, second place, third place, and fourth place. Pero for our model, kapag mas maraming or kahit pare-pareho yung proportions ng wealth ng bawat player, nagbabago pa rin yung placing probabilities for the second, third, and fourth places. Okay? So hindi siya hindi equal yung placing probabilities kapag equal yung proportions nung wealth ng mga players. So ibig sabihin nagma-matter yung exact number or yung exact amount or yung exact value ng wealth ng bawat player. Okay? So as the total wealth increases, posible na merong limit na ina-approach yan, pero hindi na kasama sa scope ng research ko yun. Pero yun, posible na may value na ina-approach yung mga to as the number or as the total wealth increases, pero keeping the proportions constant. Okay? So yung previous two slides is just a comparison for the solutions obtained using our model and the independent ship model. Next, we have an example of a calculation of player equities. So in this example, in a large poker tournament, the top 4 finishers are awarded $5,000, $2,500, $1,500, and $1,000 respectively. And after several rounds or several days of playing, only 4 players are left. Sabihin natin those players have wealths A, B, C, those players A, B, C, and D have wealths or have chip stacks 4, 3, 2, and 1 respectively. And a common scenario in this type of tournaments, kunwari tatlo or kunwari, in this case, 4 na lang kayo, it is common practice para kung gusto ng mga players, common practice na pag-usapan nila kung paano nila hatiin yung wealths, imbis na yung first place ay 5,000, yung second place ay 2,500, and so on. So ang tanong ay how do the remaining players split the prize pool equitably? So using the computed placing probabilities in our model, kaya natin i-compute yung equities ng bawat player, and dito pinapakita natin yung probability nung pag-place ng first, second, third, and fourth ng bawat player with starting wealths 4, 3, 2, and 1 respectively. And using these probabilities, ito yung gagamitin natin na weight, i-multiply natin sila doon sa price para sa first, price para sa second, para sa third, and para sa fourth place. Ang makukuha natin ay ito yung equity ng players A, B, C, and D. Okay? On the other hand, ito naman yung price split para sa 4 players using ICM. So yung player A, price split niya ay $3,177 as opposed to $3,213 in our model. Pero yun, magkalapit naman yung mga magkalapit pero hindi sakto yung mga player equities na solve natin dito. Okay? And we also compare between N-tower models and how expensive or yung expensive dito na tinutukoy natin dito or yung cost na tinutukoy natin dito ay yung number of operations involved in setting up or number of operations in kunwari in solving the linear system. Okay? So in this case, for n equal to 4 and s equal to 6, yung model ni Bros, kung yun yung gagamitin natin, we will have this this tetrahedral lattice for n equal to 4. So ito yung lattice natin, and marami tayong mga stage dyan. Papakita natin sa next slide kung ilan yung number of terminal and non-terminal states galing dito. Pero for our model, ito lang siya. Okay? So meron tayong 4 na non-terminal chip positions, and meron tayong 9 na terminal chip positions. Okay? So dito, ilan yan? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Meron tayong 10 na meron tayong 10 non-terminal states, tapos meron tayong 40 na terminal states. So mas marami. So dahil mas maraming nodes, mas maraming mas maraming nodes or mas maraming vertices, mas marami rin yung edges na mako-construct natin, and dahil doon mas malaki yung matrix or matrices involved doon sa linear system natin. So for example, in this specific scenario, nandito tayo sa case na to. So n equal to 4 and s equal to 6. So ito siya. So for Bros, number of operations involved ay 11,000. Sa model natin 1,000 lang. So 91% yung savings sa number of operations sa pag-set up and evaluate ng linear system. So yun, as s and as n increases, mas marami pa or mas malaki pa yung savings natin in the number of operations. Okay? And as a summary of results for a positive integer n greater than 1 and for positive integer total s, nag-construct tayo ng multigraphs showing transitions between possible states. Yung matrices, kinonstruct natin mula sa multigraphs na yun. And from those matrices, sinolve natin yung placing probabilities galing dun sa constructed linear system na yun, and by using a recursive algorithm. And solutions depend on actual number of chips and not just on proportions. And this differs from the ICM or independent chip model tulad ng pinakita natin kanina, and models using Brownian motion in earlier models used by Bros, for example. And expected time until ruin was calculated using the fundamental matrix for the absorbing Markov chain. Okay. And compared to the Bros N-tower model, the multigraph model or our model uses smaller matrices in computations, yielding considerable savings in the number of operations. Okay. And what are possible recommendations or ano pa yung mga possible researches na pwedeng gawin as extensions of this research? Number one, pwedeng i-vary or pwedeng i-vary yung bet size depending on the wealth of the players or the pair of players involved in each round, with the possibility of bet size selection following a distribution other than the uniform distribution. So dito kasi sa model natin, sa N-tower problem, kapag may na-select kayo na player, na dalawang players, laging 1 lang yung wealth na nata-transfer between those two players. So kung sino mananalo, makakakuha ng 1 unit of wealth galing dun sa losing player. Pero in a possible extension, kunwari yung dalawang players na yun ay may wealths na 4 and 3, for example, posible na more than 1 yung mawi-wager or mabibet nila in one round. So pwedeng 1, pwedeng 2, or pwedeng 3 units of wealth yung matransfer in one round. So that is one possible extension. Posible rin na i-apply yung algorithm to solve other n-player game variations, which are yung other common game variations are symmetric games or player-centric games. So symmetric games are games wherein all players are involved in each round. So for example, you have 4 players, in each round, lahat ng 4 players na yun magbe-bet ng 1 unit, and the winner in that round will win 4 units of wealth. So makakakuha siya ng +3 galing doon sa 1 unit na binet noong other 3 players. Okay? Player-centric game naman ay isang game variation kung saan kunwari si player 1 lagi siyang involved doon sa bawat round, and kunwari 4-player game, either player 2, player 3, or player 4 yung mga kalaban niya. Pero in each round, laging involved si player 1. And another possible recommendation is obtain a formula for the expected time until ruin for n greater than 3. Para kasi sa 3-tower problem, meron ng formula na nakuha para sa expected time until ruin. So yan, pwedeng hanapin kung ano yung formula na yun for n greater than or equal to 4. Okay? So here are my references. So if you have questions or clarifications, I will be glad to answer them. So thank you for listening.
Okay, thank you very much to Dr. Marfil. Let us all give Dr. Marfil a round of virtual applause. Thank you. So do we have any question from the participants? Meron po ba tayong questions from the participants or from YouTube? So any questions here? Yeah, I have a question. Doon ba sa in the BRUS model, do they also give the same output na yung placing probabilities? Kasi I think you've only shown the comparison between the number of operations, right? But in terms of the output of the placing probabilities, are they the same?
Yung BRUS model kasi hindi nila kayang mag-solve ng placing probability. So
Hindi ba?
hindi niya kaya mag-solve ng placing probabilities. Pero kung yung in terms of matrix sizes, kung kunwari yung pag-setup lang mismo ng matrices, yun, mas maliliit yung matrices na nako-construct gamit yung model ko. Pero ang isa sa mga advantages naman ng BRUS model ay posible kasi na hindi fair yung game. So kung hindi fair yung game, kung nagmamatter kung sino yung player 1, sino yung player 2, player 3, and player 4, doon pwedeng gamitin yung BRUS model, and yung model ko naman yung hindi pwedeng gamitin para doon sa mga ganong types ng games.
Yes, thank you. Are there questions? Other questions?
Okay, pwedeng magtanong?
Yes po.
Okay.
Sino po ang nagsalita?
Kasi
Sir
ako,
Perry.
hi.
Si Sir Perry, hello po.
Oo. Magtatanong lang ako kung may variants na sa literature itong n-player games mo. Yung isang naiisip kong variant ay paano kung may possibility at any time na ma-take out yung say yung wealthiest player. May ganung variant ba?
Hindi ko po siya inaaral kasi ang isa sa mga assumptions dito sa mga isa sa mga assumptions para sa ganitong types ng problems ay constant yung wealth total.
Yes, pero yeah. So may gumagawa na ba doon o wala? Kasi kung wala, di magandang opportunity.
Baka po. Pero hindi, parang wala po yata ako nakikita na wala pa po ako nakikita ng ganun. So possible, yes.
Yes, or posible ba na I think isa pang variant na naiisip ko ay pwede bang at some random time mag-reset yung wealth to some original state na nearly balik sa nearly equal? Diba parang nagka-revolusyon o yung mga ganong variants baka pwedeng parang kung marami ka namang undergrads na naka-assign sa'yo, di at the minimum ang pwede mong gawin parang simulations lang kahit wala mo ng analytical results, assign mo yun sa undergrad. It might mga relatively low risk na
Possible, sir. Opo.
Yeah. Kasi ang motivation nun ay dun sa ginagawa ko, yung dalawang recent interest ko ay, okay, paano kung may possibility of death? Paano kung may possibility of resetting? So yun yung nakikita kong closest na approximation ng ideas na yun dito sa problem na to. Pero so wala masyadong literature doon kasi kasi nga 'di ba kung may probability of resetting, may possibility ka nga na hindi mag-end yung game eh.
Opo.
If that resetting happens sufficiently, if that resetting is of sufficiently high probability of occurring. Ayun lang.
Yung usually po kasi yung mga ganitong types ng problems involve tournaments. So sa poker tournaments po usually constant yung chips in play, kaya hindi po usually hindi pwede yung may isang player na matatanggal.
Oh, okay. Okay. May isang variant ako naisip, no, na halimbawa kasi 'di ba may placing. Pero halimbawa habang ongoing yung tournament, illegal pala, biglang na-raid. 'Di ba? Ditigil bigla. So tapos noon, let's say yung placing mo dun sa mga natitira, i-base mo sa okay, sino yung may highest wealth at the time na raid, next highest. So how may ginawa na bang ganun?
Yun po yung isa sa mga ine-estimate nung ano.
Yeah, pero yung placing niya ay ang assumption ay at this point, kung kunwari tumigil tayo dito sa point na to na ang wealth natin ay 4, 3, 2, and 1, kapag tinuloy ba yung game, ito yung probability na first, second, third, and fourth, pero dahil natigil yung game at for some reason, kunwari na raid nga, yun, doon na siya, parang, yun, isa rin po yun sa ano, yung pagtigil po ng game, isa rin po yun dun sa yung mga scenarios kung saan magde-decide na lang yung mga players na split na lang yung total prize pool among themselves. Yeah. Pero baka pwedeng ma-motivate yung nababawasan yung player. Halimbawa may suspicion yung host ng tournament na nandadaya yung top player.
Pwede nga.
Anyway, sige. Yun lang.
Baka po posible siyang magkaroon ng applications sa imbes na poker tournaments, pwedeng cash games. Dahil yung cash games po ay at any point, posibleng may player na pumasok or lumabas doon sa game. So, possible po na doon yung applications niya.
Okay, thank you. Yun lang yung mga tanong ko.
Thank you po, Sir Perry. Do you have any other question? Sir Ernie, I think you raised your hand earlier.
Yes, I did. Hello, good afternoon. Good afternoon, Perry. It's nice to see you here. Pero sana yung motivation ay hindi yung raid or something. I mean something more legal yung setup. But anyway, no, my question really is because there seems to be several models being used, no? Have you thought of a way to validate your computed values? Say, kahit na super dumb lang siya na simulation, you run it so many times and you check the final outcome and you counter-check it with your calculated probabilities, no? So you can let the program run for ages and let's say after a week, you've made, kasi ano yan pwede mong ma-program yung game, di ba? And then you collect all possible outcomes. And then you have you can compute for probabilities kung ano yung final state and so those things, have you ever done such? It matters no, especially if you have several models no to compute, in the end alin doon yung pinakamalapit sa tama in the absence of analytical results, no? So I think it makes sense, but of course streamlining that exercise, no, that simulation will matter also kasi nga alangan namang ilang linggo mo siya i-run. Have you done something like?
Hindi pa po, sir. Pero ang sinasuggest niyo po ba ay parang Monte Carlo simulation?
Well, yeah, something like that, of course.
Possible po, sir. Pero hindi ko pa po siya na-try.
Pero hindi ba siya nagma-matter? Kasi in the absence nga of the actual true, no, the true values, how can you claim that your model is superior to the existing? Other than saying na mas konti yung laman ng matrix, mas konti yung number of calculations involved. Pero syempre, no, I mean, para sa OC tulad natin, we want to know what really is the actual probability. So, di ba mas ano yun? Mas important question na sagutin.
Sir, yung dito sa solution naman po natin na ginamit ko ay exact values yung ginagamit. Na yung nako-compute, hindi naman po siya yung asymptotic solutions na lumalabas galing sa ibang models. So, yun. Ganun po siya. Parang exact values na po siya lumalabas.
Sorry. Baka mali lang yung intindi ko kasi hindi ko nagigets yung buong kwento. Pero kanina, di ba, merong yung final na distribution ng pera and then pag ganito yung model, ito yung distribution and then you also have your own calculations. So definitely, you cannot claim that yours is the correct answer kasi may isang sagot din doon. Tama ba? So but you know, so how do you argue that yours is the closer to the actual?
Yung ano po, yung ICM po kasi ang assumptions niya doon ay yung game ay mag-end doon sa time na yon mismo. Tapos conditional probabilities na po yung ginagamit niya regardless of game structure na siya. So kahit anong game structure pa yung gagamitin, yung ICM, same values yung ibibigay niya.
Sagot. All right.
Kunwari, 4, 3, 2, 1, hindi dependent kung four-player game or player-centric game or symmetric game yung game structure. Same values yung ginagamit, yung mabibigay niya. Pero yung model ko naman po, specific for the N-tower problem lang. Yung sa isang game variation lang po. Dahil ganun po siya. Yung ICM, yung independent ship model na usually ginagamit, wala po siyang specific na game variation. Parang estimate lang talaga siya from the wealths of each player.
Okay, thank you. Salamat.
Okay, do we have any other question? Ay, sorry, ako na lang pala, curious lang. Kasi nabanggit nyo kanina, you mentioned earlier that in your model, medyo nagmamatter yung exact amount as in contrast do sa proportion sa ICM. Pero tama ba yung nakita kong numbers? Pero parang nalalapit naman yung mga placing probabilities. Hindi naman sila nagkakalayo.
Malapit naman po. Parang meron siyang limit na hindi ko
Oo nga or at least kasi baka iniisip ko kung may insight baka yung nakuha dito, baka mamaya it's just something numerical lang pala yung kaya may mga pagkakaiba. So I think it's also worth checking out or ayan. So kung may insight na kayo doon or what. Pero ayun nga, nabanggit mo naman kanina, I think magandang investigate yung limit niya or kung ano yung property na nangyayari dito. Oh, and we have a question here in the chat box. Just curious whether you can apply some Perron-Frobenius theory to your study from Sir Manju po.
Wait, di po ako familiar or kailangan ko po yatang basahin muna yung theory na yon. bago ko masagot yung question. So, ay naka-mute po kayo, Sir Gino.
Sorry. So it seems natural with the matrices you are working with.
Tingnan ko po yung theory na yan.
Thank you very much. Okay, so yeah, maybe we'll stop here. So again, let us all give Dr. Murphy a round of virtual applause. So thank you very much, Dr. Murphy, for giving us this nice talk. Okay, so our next webinar will be on October 11, and we'll be hearing from the matrix analysis and linear algebra group of our institute. Okay, so till then, thank you very much, and I will see you. So have a nice week ahead. Bye.
Thank you po.
So thank you all for being here.
Thank
Thank you again,
you.
Dr. Murphy.
Bye.